Okay, so good morning. This is the second formal lecture that you need to do different work here. And there's a point in why I did this. Because what I was trying to show is that when you try to understand things like protocols and networks, something that's happened very recently is you try to understand them as formal systems. Okay. And that was one of the approaches that most of people still follow. There are 4 or 5 groups now that do that. So today we're going to hear him on this colloquium, which is model-based systems engineering, and in particular building algebraic structures with combinators. To repeat his introduction, he was in this country until about 2005 with Bell Labs, where he was working on routing protocols, and then he moved to Cambridge in the computer laboratory, where he studied formal models and algebraic modeling of various systems, including routing protocols for various systems. So today he's going to talk again about building algebraic structures with combinatorics, and Tim, we enjoy having you here, and I hope you can thank you for having you more than the formal lecture. And there will be an additional informal lecture sometime tomorrow or Wednesday, as the one that we did before.
And again, I will be here until probably Friday at noon if you want to talk to me. So.
This is next door to Sam. This is 2251. Room 2251.
And we are having a roundtable on this because we can do that other thing in a half an hour.
Yeah.
Okay. At 4.
At 4.
Okay. So this is work that a lot of the actual physical labor of this talk was done by Vilius, who was a student who just submitted his dissertation a few weeks ago and vanished to Google in London. He did a lot of this work, and I'm on sabbatical now, and I'm sort of continuing this work. I'm going to spend most of my sabbatical working on this system that I'll describe today. And I'm going to just say that, you know, the basic motivation here was the use of semirings in network path problems or algebraic path problems. I want to describe sort of generalizations of shortest paths in graphs, and we start with this min-plus structure, and we generalize that to a huge family of semirings, and we can do a lot of interesting things with that, including finding globally optimal paths and etc. But I won't go into a great deal about this. I talked about it last week. I'm just going to throw this one slide up there saying, you know, there are many semirings out there. I'm going to just talk about this problem. So if you want to see an encyclopedic survey, this is, I would cite the Gondran in the notebook. But now, here's the problem I want to solve. You have some large collection of algorithms, let's say Dijkstra's algorithm, Bellman-Ford. Maybe some of these are implemented as distributed algorithms, let's say something like link state in a network routing context, or you have something like a path vectoring algorithm, a distributed algorithm for computing one of these semirings. So there, just for Bellman-Ford, I can think of 5 or 6 variations of Bellman-Ford alone, both centralized and distributed. Also, they vary a bit on what algebraic properties they require. You know, do you require distribution left or right, or both, right? And do you require certain special elements to exist in the structure? And then that's just for global optimality. If you believe in local optimality that I talked about last time, then a lot of these algorithms have local optima versions as well. And so the actual choosing the right algorithm for your semiring is a kind of a complicated thing in itself. And now you're going to construct some complex semiring, and now you're going to have to prove that this property holds, and then I'm going to match it up with this algorithm. And so this is the kind of this problem of constructing new semirings, complicated ones, and checking their properties is the part that I want to automate. Okay. Because the original motivation for this work was we want network operators to be able to design new routing protocols and just configure them on their routers instead of waiting for this long standardization cycle and having Cisco buy into it and actually implement the protocol. I want network operators to just be able to configure the new protocol and then have the configuration checker or implementer, the compiler essentially, check whether the protocol has the right properties to use with this algorithm, right? And also I think in the operations research area where there's a lot of use of semirings for finding paths, you know, I'll get to it, I'll show you an example at the end of the lecture that's actually quite difficult to prove properties about. It comes from an OR paper in an OR journal from just a few years ago, and it's actually a very complicated semiring, and the author spent an enormous amount of time actually proving that it is a semiring. And in the system I'll describe here today, we can just write down a 3-line description of this thing, and the proofs come out automatically. Okay, and we can get code that implements the semiring. Okay, so basically I want, and this is a little bit fuzzy, right? I want to be able to define. I want a domain-specific language for defining algebraic structures that automatically I can extract the code out, and I can run these things, and I can also be sure that I've matched them up with algorithms in the proper way. So when I say properties, here are just some of the properties that an algebraic structure might need to, for example, use Dijkstra's algorithm or Bellman-Ford. And for example, we don't have to look at all of these. So for shortest paths, this times here is plus, and this plus is min. Okay, so you have to make sure that times distributes over plus. Those are the 2 distributivity rules, and then there are a bunch of other rules. And like I said, I sort of threw these things into this set. Some algorithms require some, I mean, for example, Dijkstra's algorithm requires some subset of these rules. Bellman-Ford requires some other subset of these rules. These are just the rules that I'm going to start off with, right? So this is my basic, I'll call this my initial root set of properties, and they're motivated by the set of algorithms that I have and consistency, okay? So this is what I want to do. And again, this is kind of fuzzy. I start off with this initial set of properties, P0. And now I want to find a language, L. And what I'm going to do is I'm going to define this language as a language of combinators. So if I have 2, let's say, semirings, I can just put them together into a new semiring. That might be the product of the semirings, a direct product. It might be a lexicographic product. It might be a disjoint union of those 2 semirings. I just have these operators that I operate on algebraic structures as wholes. I don't go down and program. I don't want a language where I program the plus and the times individually. I'm going to start out with a library of things like min plus, max min, things like that. I start off, and then I put them together. Okay. So I'm gonna have some well-formedness condition on these expressions in L, and I'll describe that a little bit later. Okay, and then I want to construct a set of properties P, which is going to include my initial P0, so that for every property P and every expression in my language, if it's well-formed, then the property holds or it doesn't. Now you might say, oh, but Tim, you know, that's trivial. That's true always, right? Q or not Q, right? Well, I'm working in a constructive logic here. So what I mean here is that I actually have a function that if I have a well-formed expression, it tells me, does it have Q or not have Q, right? So this is it's essentially a decidable property. In general, of course, if I give you if I wrote down an arbitrary semiring in some mathematical formalism, it's not decidable. For even things like left distributivity are not decidable in general. So I'm going to decide. I'm going to come up with an algebraic language, a domain-specific language, where all of my properties are decidable. So you, the user, you want to write a new semiring, you write down this, you write your expression, and the system will tell you yes or no. It's left distributed or it's not. Does it have the properties required for Dijkstra? The system will tell you. Okay. Now, why did I put this P0 is in P? Well, the thing is, you start with an initial set, and then as you add constructors to this language, you have to throw in other properties, as we'll see, in a way that we'll see. And so this the set of properties you're actually working with can grow very large as it has. Okay, so that's sort of the basic idea of what we want to do. Okay, so let me just give you an example of a language that I'm gonna talk about, and this is a really small subset of the language that we have, and it's just for structures of this signature. This is a set, a carrier set, a binary operation, 2 binary operations on that set, and I'm going to call these things bi-semigroups. So they're not quite semirings; they're really weak things. And I just have this little grammar here where I have constants that are min plus, max min, and then I'm going to add a multiplicative identity, that add 1, or add 0 is an additive identity, or I'm going to take the lexicographic product in one way or another. So that's the basic idea of this kind of language. Now I'm going to tell you what each of these operators means in terms of how does it construct. So if this represents one of these bi-semigroups and that represents a bi-semigroup, how am I going to construct the bi-semigroup of these things? And this little language is based on some very simple operations. So for example, if I have circle there as a binary operator, well then IDC circle is a new binary operator that just adds C as a disjoint union. There's a tag, that disjoint union is just a tagged union of sets. It just adds a new constant and treats that as the identifier. As the identity operator of a new operation that I've just defined in terms of my old operation and this new constant, okay? So it just adds a thing that acts as the ID. This operator acts in the same way, except it introduces an annihilator. So now, if this new operator is, I take a constant in the old operator, then C now acts like an annihilator. Okay, so in terms of min, infinity is an annihilator. So anything min infinity is equal to that thing. That's the ID. 0 is an annihilator for min, sorry. 0 min anything is 0, okay? So that's the kind of thing we want there. Direct product is, if I have 2 binary operators, I can just define their direct product. That's pretty simple, okay? So, and then finally, this is, for these operators, I can often think of them as these binary operators, like min and max, or union even. I can often think of they're being associated with a partial order. Okay, so if I have 2 partial orders associated with these semigroups, then I can define a new semigroup that is the lexicographic partial, the lexicographic semigroup that has the lexicographic order, as you would imagine it, associated with it. And this, who cares about the details exactly about this thing? It just, think about it this way, it compares these 2 guys and sees, well, which one is bigger? And if S2 is bigger, then you get this guy, S1, T1. If S1 is bigger, then you get S2, T2. And there are some other cases for who really cares. It's
to connect to some of the things that we discussed in this colloquium and we have done, is that the lexicographic order is particularly useful for trade-off analysis. I hope you see that.
Yeah.
Because this is perfect for when you have more than one matrix and you want to start comparing either pairs or even tuples, but you don't want to combine them. You just want to order them according to certain preference relations.
So we've spent a lot of time studying lexicographic products in different contexts because if you reverse engineer internet routing protocols, you will find lexicographic product buried in every single protocol. Even the ones that people think of like OSPF and ISIS, they think, oh, these are shortest path protocols. They're not. When you look at the metric they're actually using, they have a lexicographic product. For example, if you're familiar with OSPF, if you have 2 routes, If one is inter-area and the other is intra-area, you always prefer the intra-area route over the inter-area, no matter what the distances are. So there's where it's buried in OSPF. And similar for all of the other protocols, there's a lexicographic product buried. And so we've lavished a lot of time on.
If I could say, just to connect system engineering, okay, so as many of you know, if I have discrete sets, discrete time, sort of path is equivalent dynamic programming, right? So now imagine if I have several metrics and I want to do all of them dynamic programming, then you end up with doing quote unquote shortest path. Like, you cannot say shortest path because you have many metrics, but you are forced to consider trade-offs. And again, so whenever a team says shortest path and so on and so forth, in these places where you have tuples, think in mind trade-off analysis, multiple rules, things like that I can use this for.
Okay, so now that we have these things defined, we can define what I'll call the untyped semantics for this little language. And that is, again, you, the programmer, all you can do is write down these expressions, and we, underneath the hood, build the right thing. So for example, add 1. You give it a constant and an expression, and if that expression is one of these bisemigroups, then what you do is you use the constant as the additive annihilator and as the multiplicative identity. Okay? And exactly the opposite for add 0. You take that constant and you make it the identity of the additive component and the annihilator of the multiplicative component. So these are the kind of symmetries you often see in semirings. Okay? And then lexicographic product is just a lexicographic on the additive component and direct product on the multiplicative component. And that's typically the way things are done in routing protocols as well. You have a multiplicative component, multiple things, distance, bandwidth, etc. And you just do a direct product on the multiplicative component, and then you compare things lexicographic. Okay? So, and the reason that we have this selective thing in here, it has the same untyped semantics, but now we're going to talk about imposing a type system on this. And in other words, we're going to restrict the things, the well-formed things you can write, and the simple, this is going to have a different typing rule than the other lexicographic problem. Okay, so what about this typing semantics? Here comes essentially trick number 1. Okay, in making this work. And basically the type semantics says when something is not well formed, you get an error. Okay. And what does that mean, not well formed? Well, when it's not, what our type semantics gives us for every expression, it gives us a well formed expression. It gives us one of these bisemigroups. And it gives us a set of proofs, 2 sets of proofs. The first set of proofs is all of the required properties for that particular algebraic structure. And these are related to the well-formedness things because you want to guarantee that these things hold, and sometimes you need to impose some conditions to guarantee that the required properties hold. And that's where the well-formedness conditions come in. And then we have these proofs or refutations of optional things. So for example, suppose something like commutativity of the multiplication is optional. Well, then we would either have here a proof that it is commutative or a refutation, a proof that it's not commutative. Okay. Now here's the key idea. Where do we draw the line, right? I mean, really, I could make this set empty and put everything in the required properties. All those properties you saw in that initial thing for semirings, we throw them all in there, right? And what happens, and by experience, sort of iterating on this design process, we found that that doesn't work because you want to be, first of all, it's very semirings have so many properties, it's very difficult to actually construct new ones out of old ones without making the constructions incredibly complicated. Okay, so we'll see an example of this. Okay, and then the more properties, required properties you have, the easier the things are to work with in some ways. The easier it is to reason about them because you have more properties to work with. So it's kind of a design trade-off to decide where that line goes. And for these things that we're calling bi-semigroups, well, guess what? The only thing we require of required properties that both operations are associated with. So we don't require any of the other properties of semirings, okay? And it turns out that this gives you a much more flexible language, much easier to work with, and it also gives you an ability to define these operations really cleanly, okay? So we'll see a little bit of that. And exactly where that line is, again, it's a design thing. And I'll try to emphasize that. So, what if we wanted to know whether this lexicographic product of two bi-semigroups is left distributive? Okay? Let's just look at that example. So here's the basic way we go about attacking this problem for every combinator. In this case, the combinator is lexicographic product of bi-semigroups. For every property, P, in this case it's left distributivity, right? We come up with a well-formedness condition on the sub-expressions of the constructor. And in this case, the well-formedness better guarantee that lexicographic product is associative. That's all we need. And it turns out that the lexicographic product that I showed you is not in general associative. You have to assume some things about the operations, the binary operators that it's combining in order to get an associative operator. So we're going to have this well-formedness that guarantees the required properties of the thing we're constructing here. And then we find an if and only if rule that says the properties of the construction are true if and only if some things are true about the arguments to the construction. Okay, then what we do is we turn that if and only if rule into two bottom-up rules. That's what we call them, bottom-up rules. So in other words, if I know that it's all the arguments are, if I get well-formedness and beta is true, then P is true of the construction. How do I know if not P is true? Well, I look for not beta on the arguments. And remember, by induction, I'm constructing this language. By the way, beta here is a Boolean combination of my properties in P. So every property in P, I can decide it, right? So by construction, you give me an expression, I just apply these rules just like a type system in a bottom-up way. And if I have these rules, these two rules for any P and C, right? Well then, I can just construct them in a bottom-up way, okay? That's trick number 2. Okay. So trick number 1 was realizing that you don't want to have all properties be true. You want to have wiggle room, okay? And trick number 2 is arranging things that in this way. Now, what this means is you're not going to have this language, whatever this language ends up being, you're not going to be able to express all semirings in this language, okay? But the thing is, we come up with these constructors. So how do we come up with an initial set of P's? We look at our algorithms. How do we come up with constructors? We reverse engineer protocols that we see and OR papers, as I'll show you later. We look at interesting semirings that are defined, and we try to reverse engineer them so that we come up with these simple operations. Okay, so here we go. Oh, and another thing. I want to work constructively, so this may seem a bit odd to you if you're not used to working in constructive logic. But so for example, if I have a proof and I know that something is not distributive, right? What does that look like? It looks like not for all blah, 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 right? Well, I actually want to introduce constructive realizations of those things. So for distributivity, I want to actually introduce a property not left distributed that has an existential quantifier there. Because if I have a constructive proof of that existential, then I have 3 witnesses that witness the lack of distributivity. And the thing is that in a design environment, if you're a programmer and you're writing an algebraic expression, and you want to use, let's say, Dijkstra's algorithm, and the stupid tool says, no, sorry, it's not left distributive, you're going to be a little annoyed, right? If it doesn't actually give you an example of, give you 3 things where they don't distribute, because otherwise, you have to figure it out. And so, in other words, if it's not left distributive in this case, if that P is left distributivity, we actually want to exhibit to the user the witnesses that prove that it's not left distributive. And so, again, we're trying to think about in a design environment where the users that are specifying these algebraic structures don't necessarily have the training to do all of the proofs, okay? Or actually, they may not have the training to do any of the proofs.
This would be like a counterexample.
It's a counterexample, right? It's exactly.
So it's like model checking.
Well, it's like model checking, but it's not model checking, right? It's not based on Buki automata. It's based on, think of these rules as brute force, okay?
But can you show the counterexample with respect to the problem the person's trying to solve?
Yeah, well.
I mean, if I want to use Dijkstra's algorithm, I want to use it to solve a specific problem.
Well,
can it explain why? Or
yes. So what I'm doing, we'll see an example. These things are all going to be in specified in a particular. I'm going to define a particular expression. That's my algebraic expression, and it's going to be the counterexamples are going to be with respect to that expression that I'm trying to specify an algebraic structure. Okay, so we have all of these sort of, and in other words, for our property set P, we duplicate it. For every property, we have a negative property that can be used constructively. And just for example, for associativity of my lexicographic product, here's the well-formadness condition. So it's the well-formadness condition for left distributivity, lexicographic product. It turns out that you need plus of the S part, the first part, to be commutative. You need it to be idempotent, and you need T to be idempotent. Okay? So it might not be obvious to you that that's true, but it's what you need to get associativity out of that lexicographic product. And now here's that rule that I told you about, the if and only if rule. So if I have the well-formadness condition, which is that thing at the top, so that guarantees the, remember this thing, the additive component is going to be the lexicographic product of the additive components, and the multiplicative component is going to be the direct product of the multiplicative components, okay? So given that it's well formed, that the additive component is going to be associative, then if S is left distributive and T is left distributive, and one of these conjuncts is true, then the original, that's if and only if that thing is left distributive. So we have to look at that. Now guess what happens? This is how your set grows, your set of properties grow, because
Where did these things come from?
well, it came from sitting down, scratching one's head. Believe it or not, it took us probably 6 months to come up with this rule. We had sufficient conditions for a long time. They're easy. But we want if and only if conditions because we don't want the design tool to say, I don't know. The worst possible thing you can have for the design tool is, oh, okay, I'm going to use this, I'm going to use Dijkstra's. Is it left distributive? The tool says, might be. Then you stop using the tool, right? So with these if and only if rules, it'll tell you yes or no. Did you have a question?
How do you come up with? No, but
Actually, we found an article on.
there must be some revision
It was painful work, okay? And we got some hints from a 1971 paper that a mathematician wrote about ordered semigroups.
Okay.
And that gave us our first hint on this condition, these two conditions, this condition, and that condition. But then we generalized, because we're working in a more general thing, we had to generalize that result. But the thing is, look, this introduces some weird new conditions like smile, which which I think is a bizarre condition, but there it is. But the other ones, for example, LSS says that you know, this strict inequality is preserved by multiplication. That may or may not be true, right? This one says that essentially,
Is the inequality like it's a partial order or?
I'm assuming here that the order on S
Yes.
is a partial order because of these two things, the semi-lattice.
But there you product.
But this guy might not be commutative, so there may not be an order there.
No, because we had a similar condition last.
Yeah, you probably had this. This is, say, cancellative, right?
That one's gotta be wrong,
Which one?
that one.
Why?
Look at it, it's, I mean, X doesn't occur anywhere on the left-hand side of the arrow.
Which one are you talking about?
The
The
L dot
first
Z.
line.
That's probably,
It's Z cross Y equals Z cross Y,
which one are you talking about?
The
L
first
dot
line.
C.
This one?
Yeah,
Yeah.
read it carefully.
Should be X.
Oh, there's a typo.
Should be extra.
This should be Z times X. Sorry, thank you.
Should be an X.
Thank you, Bill. That should be an X.
And probably for the one below it too.
Yes, thank you very much.
Good thing we have computer checkers for all this one.
I was gonna say, you know, this one is definitely true. I thought you, because we've checked it. Okay, thank you, Bill. So cancellativity is an example. Now what you have to do, remember what we're doing here, the game we're playing. Now I just have to throw in 1, 2, 3, 4, 5 new things. And by the way, these are not properties of the bi-semigroup, right? They are all properties, actually that's not true, I've got to be careful here. This is just of the multiplicative semigroup. This is of the multiplicative semigroup. This is of the multiplicative semigroup, but there's an identity there, right? Oh, sorry, it's of the whole bi-semigroup. These less thans are actually defined in terms of the plus, and so they are actually using both things, right? Okay, so the point is,
Correct. I mean, the last one seems a little bit strange because for any X and Y, you can get rid of them.
yeah,
Okay.
it is strange. You know, some of these things, again, you just turn a crank. We want if and only if rules. You get these weird properties.
Okay, that's fine.
So now we have to throw those properties in our set of P's, and then we have to push them through every constructor. Okay? And we have to do this, we have to wash, rinse, repeat. Wash, rinse, repeat. Right? So here's just an example of a current snapshot of where we are right now. We're not, as we'll see when we get to this more interesting example later, we're not just restricted to bi-semigroups here. But bi-semigroups, we have currently 22 properties, positive ones. That means we have 44 properties that we're actually looking at, and we have 20 constructors. So that means, you know, 20 times 44 theorems have to be proved. Okay? For those bottom-up rules. We have these other structures. I'll talk a little bit about them. For example, semigroups, pre-orders, ordered semigroups. We have these other things that, if you're familiar with routing protocols, you actually put functions on arcs, not weights. And you transform metrics as they come along with those functions. And that's what these transforms are for, and these ordered transforms and so on. They're for modeling things like route maps in BGP or route maps in Cisco parlance. But anyway, so just in this snapshot, we have 1,700 bottom-up rules. Each one of those has to be proved. Now, here's what happened a few years ago. I came up with this idea of this Combinator language in about 2005, 2006, and started implementing it by hand. And sort of proving all these things by hand. I had a little LaTeX document and proving all these things by hand, but it's a design thing. You know, we kept changing where those lines were, where, you know, what was required and what wasn't, and you know, the thing became unmanageable. And as a graduate student, I worked on an interactive theorem prover at Cornell. It was called New Pearl. And when I left Cornell in the late 80s, when I drove out of Ithaca, New York, I said, I am never touching another interactive theorem prover in my life. You know, I was sick to death of my dissertation topic, and I just didn't want to know anything about these things. So, but when I ran into this problem, you know, I was a little bit stubborn, right? And this is about 2007 now, 2008. I really didn't want to use a theorem prover because I thought it would kind of make it harder for people to use this tool, okay? But I finally gave in because the more constructors we added, this number kept getting bigger and bigger, and I said, oh, we need some automation here. So I got over my hang-up, my anti-theorem prover hang-up, and I said, okay, we're going to use a theorem prover. And that's what Vilius, and then Vilius started his PhD, and he's the guy who started using this. But we spent, so the theorem prover is called the Koch theorem prover. This is from INRIA. It's been under development for about 25 years. It has a huge user community. And it's a very nice system now. So we chose Koch because it has a higher order logic, it has a constructive logic, which is really important for us. It has this extraction mechanism that I'll talk about. You can actually, the system is implemented in OCaml, which is a dialect of ML, the ML programming language. And if you have a constructive proof, you can extract out ML code that implements that proof, okay? So here's what we did, and I think it's kind of a novel use of the extraction mechanism in Koch. We proved that semantic function. Remember that semantic function I talked to you about? So from the syntax of by semigroups, now this is just a data type in Koch. It's an inductively defined data type. And we've implemented a semantic function that gives you the representation in the Koch, you know, it gives you a Koch function here, a Koch function there, a data type in Koch, gives you all those proofs. We implemented that in Koch as a recursive function. Now what we do is we extract, using the extractor, we extract out the ML code. And now in ML, we have sort of a version of this thing that we can run. And the advantage of doing this now is once I have all this code, you, the user, you don't need Koch anymore. In other words, we, at design time of this combinator language, we do all the proofs at design time. You, the user, you just run this code. We can distribute the system as just OCaml code. You never have to load, you never have to run the theorem prover. So we figured this would, you know, we're trying to attract network operators and so on, right? People from Cisco, right? And just the idea of getting this thing running and that they're going to have to use this thing is terrifying. So we want the system that they don't have to use the theorem prover. We do that for them. Okay, so this function, essentially, remember I said there are 1,700 bottom-up rules now? Well, this function in ML now implements those. You know, courtesy of this extraction mechanism and courtesy of Vilius's hard work in proving all those theorems like that. So now we have a little shabby, right now it's very shabby interface around this, and it's very shabby because I implemented it. It takes, you know, it's got a parser and things like that, and then it feeds the syntax tree in here, gets this stuff out, and we can use it. Right now, all of the algorithms have been implemented outside of the system. And sort of the meta theorems that Dijkstra needs this and that are all outside of the system now. Currently, I'm sort of gradually trying to migrate some of the algorithms into this part and prove properties of the algorithms. But so far, we're just doing the language bit. Okay.
When you say outside the system, is a different
For example,
languages and software and
so I have, for example, Dijkstra's algorithm implemented here. I've implemented it, and I've said, oh, Dijkstra needs this property, that property, that property, that property. And now if you use Dijkstra's algorithm on the thing you get out here, the system checks, does it have the right properties? But I haven't actually proved in this system that Dijkstra's algorithm needs those properties in this and that.
side knowledge.
So I'm trying to be honest here, right? What the system does and doesn't do currently. Okay, so here we go. We're going to have a little example. I'm going to run through this really quickly. We have this system is called MRE, which stands for Meta Routing Environment, but it's pronounced mystery, okay? Or Mr. E. So I have a little variable here. I assign it to, really these expressions right now in the current system, it's so shabby, it's really just abstract syntax. It's not real syntax. It's just, abstract syntax trees, essentially. I'm just saying this bi semigroup that's natural numbers and max min. And the thing is, the system will actually poop out, 60 or 70 properties, and I'm just showing you the interesting ones. This is the kind of thing, it knows the properties. For example, there is an annihilator. It's true, there is an annihilator. And there's the witness, because having an annihilator is an existential statement. There's the witness. This one, the existential statement for this guy is there exists A, there exists B, and so there are the two witnesses that inhabit that thing. Okay, so not so interesting. We do nat min plus. Now we do something interesting. We add 1 to this. And remember what adding 1 does? It makes that new thing we're adding, that inf, it makes it an annihilator for the additive component and a identity for the multiplicative component. Okay? Not very interesting so far. We add 0 to, so what I did is I added 1 to max min, I added 0 to min plus. Now, essentially, by the way, let's see, what am I doing here? Both of these things are now semirings. They have all the properties of semirings. Now I want to put them together in a lexicographic product. Boom, here I put them together in this lex product, so I had this, I just defined SP, shortest path, bandwidth, these are two semirings, I do lex product. Ooh, they're not distributive. Okay. So this is a really good example of why we simplify, why we don't require the arguments to be semirings. Because the thing is, if you look at that lexicographic thing, there's no way that you can combine structures that have identities and annihilators and expect the thing to be distributive, right? The alternative is to make the definition of lexicographic product extremely complicated with all sorts of special cases. And then it makes it very hard to reason about. So again, the system automatically, I'm running, by the way, I'm not running calc here, I'm running the extracted code. And it automatically, remember, distributivity has a existential, not distributivity has an existential with 3 things there, and these are the witnesses that show that. So what we want to do is we want to do the lexicographic thing before we add the annihilator and identities. So here we back up a little bit, we do the lexicographic first on these things, and we get distribution is true now. What violated distributivity were those special elements. And now we put them in, okay? So I did the lexicographic product of min plus and max min. Now I add the 0, okay? And that's the kind of, this gives you some insight into why is it that we're not requiring these things to be distributed or to be to have all the semi-ring axioms, etc. The other reason is, of course, what I talked about last week, the business of dropping left distribution or right distribution and still having local optima, right? That's another reason for not requiring such properties. Now, what if we did it the other way around? Max min, min plus. This says min plus does not have a multiplicative identity. I don't know if you noticed, but the 4th clause of that lexicographic product required an identity, a multiplicative identity in the 2nd argument. And this is where, remember I said that there's a selective lexicographic product that has a different type? Now I'm going to use that one. Because Selective lexicographic product has the same semantics, but it doesn't require this guy to have an identity because it requires the first thing to have a total order, so that that fourth case in the product, the lexicographic product, is never executed. Okay, so here's an example of operationally the code generated is the same, but it has different types because we're able to. Oh, and by the way, this one violates left distributivity and right distributivity, but we can still use it to find local optima. That's another talk. So now what I want to do, this is an example I just added to the talk, and I hope you will like it because it comes from an operations research paper. So what I want to do, the really interesting structures to reason about are these when you're dealing with sets of things and you're taking minima or maxima over sets. So suppose I had, and this sort of motivates why we have other structures like these preorders, because I'm going to show you that you can build interesting semirings out of preorders. And so we have language of preorders in our language, and then we can construct semirings from them. So suppose this is a preorder. So what I mean by that is it may not be antisymmetric, but it is reflexive and transitive. Okay, and I'm going to do the min A for a finite subset A, finite subset of S. It's just going to be the set of A's that don't have anything below them, strictly below them. So they're the if that were a partial order, these would be called finite antichains, if you're familiar with that terminology. And so now I'm going to construct a new carrier set, which is the set of finite subsets that are invariant under this min operation. Okay. So this makes sense in routing a lot of times. You have sets of the best routes you can get. You have a multiset. You're doing multiset routing. Now the operation, the semi-group that you can construct, has this funny union operator. So you take an A and a B that are of that type, and you union them together and take them in. You take the best routes from neighbor 1, best routes from neighbor 2, and you find your best routes by taking the union and minning over that. Okay? So that's a nice construction. Now here are some things we're going to build with these in our language. So, by the way, remember I'm working with abstract syntax really here, and this guy is going to build a partial order or a pre-order. This guy is going to build a semigroup. This guy is going to build a bi-semigroup. Okay, so this expression, if it's a semigroup, if it represents a semigroup, then I'm going to return the order that is one of the natural orders of a semigroup. There are two natural orders associated with a plus, and if this plus is associative and it's commutative and idempotent, then this guy will be a partial order. Okay. So the other thing I can do is I can build that semigroup I just told you about. If this guy is a partial order, if the E represents a partial order, then I'll build this semigroup with that funny union-min operation that I just described at the bottom of this page, and that's a nice associative semigroup. Okay, now how do I build a bi-semigroup? Well, what I'm going to do is I'm going to, if this thing is a oops, that should be, Bill, that should be a plus. Sorry. That's a plus.
It's giving the others a chance.
Yeah. And what the hell is that L doing there? That L should not be there, and that should be a plus. Okay. I was doing this in Starbucks this morning, so. So anyway, so the additive component is that min union thing, and the multiplicative component is, well, it takes two sets, and it just pairwise multiplies them, right? And then takes them in. So I'll describe this in terms of routing, right? I take my best routes, I take two best routes, two sets of best routes, I union and take them in. That's how I choose best routes. And to the multiplicative component along a path is, imagine that I label all of my arcs with a singleton set, right? That's one way to think about it. Is I just then take my policy on my singleton set arc and I multiply all the things my neighbors are passing me, right? That's what I get from my neighbors. So this is the multiplicative component along paths. Okay.
So that's compositional order, right?
What's that?
because you don't have, for instance, in the way you do things, you don't want to have pressure optimality or anything like that. You have to get out the system by composing the minimal sets,
Yeah,
right? Because you don't get optimality.
that's right. So I now want to use these things to do interesting things. Okay, so I got to admit, you know, these things are hard to prove those if and only if theorems about. Vilius spent a lot of time coming up with those if and only if rules for these constructions. And some of them were quite interesting, actually, and if you want to look at his dissertation, he spends a lot of time talking about them. Anyway, so here's a semi-ring that I want to talk about. It's defined here, 2003, in Quarterly Journal of Operations Research. It's called the bottleneck shortest paths on partially ordered scales. Here's the basic idea. Arc weights, the things on the arcs come from a partial order. Okay? S is better than S prime means that S is less than or equal to S prime in that partial order. Okay? A pathway, so suppose P is a path in the graph, then it's the set of the worst arc weights in path P. So this may have multiple things in it because we're only dealing with a partial order. It's sort of the anti-chain, right? It's the worst thing, so I'm looking at the worst arcs. And now I say one path P is better than another path Q if for every S in the weight of P there exists an S prime in the weight of Q that is worse. So it's bounded, you know, the weight of Q bounds the weight of P above, dominates it, maybe is a better way of saying it. Okay. So in this paper, they spend a lot of time motivating this and also proving. They build a construction and spend, you know, several pages grinding through the complicated proofs that it is in fact a semi-ring. And so we looked at this and said, wait a minute. You know, I bet we can just like we've been reverse engineering these routing protocols, I bet we can reverse engineer this OR paper and express it in our language, and sure enough we could. Now this semi-group product is just a direct product of min cross min, direct, so it's a partially ordered thing. I defined that right natural order that I talked about previously, so why the right order? Because I want to minimize this thing, but I want to do it over the dual order, so I get the worst guys. Right? This is going to be the thing that gives me the worst things, and then I'm going to take the min set union of that. So this semi-group is going to be the one that's going to give me the set of worst things over a path. But I'm not done yet, because now we've done one min set construction. I need to do another. I'm going to take this S2, I'm going to take the right natural order over that. Now that's a partial order, but remember the objects of this guy are sets of things. So this guy has sets of things in it, ordered properly, and now this guy is going to take sets of things that are minimal with respect to something or other. Okay, so we could spend some time looking at this if you want to in the round table or something, but the point is that we were able to just read the paper and think about it in terms of our language, write down this 3 lines, and boom, it's proved, right? It's a semi-ring. All the properties are there, and also in our system we could run the example that's from the paper. And this system, okay, I got to admit, the system is kind of flaky right now because of that interface that I'm writing. It's pretty flaky, but you can actually define an algebra, define a weighted graph, run something like well, in this case it was Bellman-Ford, because Dijkstra you can't use on this algebra because it's not totally ordered, but you can run Bellman-Ford and get an answer. So hopefully this allows people, either mathematically, people that don't know how to prove this stuff, that want to explore the space, or people that I think probably more productive people would be people who actually understand the mathematics and want to explore the space, but don't want to prove things. Anyway, the example from the paper is this. This is distance, and this is how dangerous this path is. So these are 2 incommensurate things. And the higher the number, the more dangerous it is. And the idea is you're traveling from along this graph, and at any point you want to, if you break down or you run into trouble, you have to go back to these nodes represent emergency centers. Okay? So the idea is you want to find paths that avoid. So for example, look at the path from 0 to 6. From 0 to 6, we have two sets in there. One is 1, 3, 3, 1, and the other set is 2, 3. So in other words, if you go this way, you're always going to, you can go this way and hit the 2, 3 guy, or you can go this way and hit both of these guys, which are not great. And now you have to make a decision. Which one is better? Okay. You mean, so the idea would be there's some external judgment call about, you know, and this path says, I'm going to be stuck, I could be stuck here in a very dangerous link, and it's 2, the distance is 2. So I might be in the middle of that, and I have to get 1 mile or whatever it is to an emergency point, and it's a very dangerous place. Well, what about this guy? It's 3, right? But it's pretty safe. This is 1, pretty safe, right?
No.
So,
One dangerous.
oh, I'm sorry. This is distance 1, but very dangerous. Sorry.
So if it's dangerous, you just have to back up on that one link.
Yeah. So these things measure to the nodes are the emergency points, and this gives you some idea about the cost of. So for example, we don't have a really good example here. They tell you something about the worst paths that you can take, a set of worst paths, and maybe you can use these now for some other algorithm anyway. So the point is, well, if we can describe this in 3 lines, I think we can do a lot in this space. And
We ran into the same problem with the min-min when we did the trusted routine.
oh yeah,
Exactly the same problem. And you have to come up with some way of deciding, right? Because you get all of these sort of ordered paths, and then you want to go through something that is trusted or not trusted, and the answer is it depends on how much traffic you carry.
yeah,
Because if you can avoid them, you will avoid them, the bad ones. But if you have so much traffic that you use them, so that actually has some very nice applications from this perspective. You know, danger is equivalent to trust. I have links that they are jumped, or I have nodes that they are suspicious that I am attacked, that they are attacked.
right.
Did you try to do sensitivity on that? This question is coming.
Oh, that would be very interesting, right?
It's coming from my.
So the other thing is here, these operations, we did not come up with these operations by reverse engineering this paper. These operations we came up naturally by looking at routing protocols, believe it or not.
Right.
We were looking at multipath routing and some of the algorithms people have proposed, and that's where we came up with these operations.
In that paper, do they talk about something like, if I wanted to now find the variable points, or select a subset of the variable points, we can take the criterion that is the one you care most, let's say in this case the danger,
Uh-huh.
start dropping links in the path.
No, they don't discuss that.
Then do the rest.
They don't discuss
This
that.
is interesting because
Yeah.
it's not commutative. If you have
Right.
min-min, and you try to do the one first and then the other,
Yeah,
and the other way, you end up with complete different sets of.
right.
You see what I'm saying now?
Yeah.
Well, this is called the epsilon Keynes algorithm. I can go and first use the one as a criteria, and I want to constrain the danger to be below a certain point, and then from those I'm going to select
Yeah.
certain spots with the other criteria.
Yeah, we could do a lot with this. You know, we could start building other structures on top of this. The one thing I really want to work on this year.
We have to take the paper I did with Kiran and try to see if we can prove it automatically with your construction.
Okay.
It's a very long paper.
Okay, let's try. Let's try. One obvious thing, if you're a programming language,
You will make me unemployed.
that's the whole idea. One obvious thing, if you're a programming language geek like I am, is you think, well, where's the what is this really a programming language? Where are the abstractions here? You know, really what I want to do is define this bottleneck thing, abstracting over this partial order, right? I want to define it as some sort of lambda, right? Oh, well then what type system do I need? And if you're familiar with programming languages, I think I need what's called an intersection type system. I need to build that into my language. And in other words, this operation, if I abstract over this guy, I want it to look just like my built-in operations. I should see no difference if now I can have a library of these things that are abstracted over things. And I can look at its type, and just as I can look at the type of lexicographic product, I should be able to look at the type of this thing. But it's not straightforward doing this, and I'm going to spend some time working on that this year. So in other words, turn this into a real programming language where you can abstract over things. And again, I want to say that we can get code out of this, right? I don't just get the type and the proof, I get the code. I can now run this bottleneck semiring. I can plug it into I can plug it into Bellman-Ford and solve problems with it. Okay, I'm going to end there.
Thank you very much. Question?
Bill.
So Tim, now that you've got these techniques for automatically composing these, can you start just like randomly putting a whole bunch of properties together and like produce the next 20 new routing protocol papers?
Yeah, that's the idea. You know, it's like Turner. So one thing I am doing is generating, adding code to generate LaTeX and generate figures. You know, and it's just a matter of time before you generate abstracts, and you automatically submit them to EasyChair. You know.
And one of the things you could do, I mean, you could do this sort of analytical approach, and then you could do some things where you say, okay, we've got these, how does this compare to the other ones? You could just do some experimental evaluations of them and sort of say, okay, experimentally, how does it compare to others?
Yes.
That might give you a different kind of insight than
Yes.
you get by the analytical.
I think that's right. And you want to do experiments, you want the environment to support experiments, and there's another thing I want to extract out of these things, by the way. I want to extract out some worst case complexity expressions. So I should be able to do that, right? By the way, the worst case complexity of this one is pretty bad, right? Because these sets can blow up exponentially in the size of the network. So the worst case complexity is bad. But you would like to know what the complexity of your algebra is, and I think we can do that sort of roughly in a bottom-up way as well.
Any other questions? So suppose that these bin sets that we have, and this is the routing, are optimal paths in the first criteria between nodes. They have some value with respect to the second.
Yeah.
And let's say the second value, exactly as in this example, the bottleneck example, is some bound or some rule about the bottleneck, which is the lower paper, or in your case the damage, or in my case the trust.
Yeah.
And now I want to say I have a subset that has some value of the, let's say, the delay, and it has a value. It has a set of optimal with respect to delay, but it has an upper bound on the trust. This was an upper bound on the trust. And now I want to put them together. Can you tell me if I still can get some way to say what happens to the first metric, and I still maintain a bound on the second? Now, can I compose that?
You know, I'm not sure. We'd have to sit down.
Can I compose trusted paths
Yeah.
this way, and at the same time compute a value for the performance metric?
I'm not sure. We have to sit down and puzzle that one out.
Because that would be very useful.
Yeah, let's try to do that this week.
Because that's where that would be very useful. Because
Right.
you can take in the case of routing, you can take pieces of nodes for which you know how to do secure trusted routing.
Yeah.
And you compose them, you still maintain some some estimates about performance versus the distributed. One question.
So like any domain-specific language, right? This is not Turing complete or anything. And so what it can do and what it can't do is often, you know, you have to just learn from experience and look at a lot of examples. You know, where is the boundary line between doable and not doable is not very well defined.
And the other question I have is, you saw our paper on sensitivity, right?
Right.
Okay, so this was motivated by trying to find out if I'm an attacker, let's say again the same example is here, and I want to make your life difficult, meaning I'm going to interfere with the damage. I'm going to start making the sets that they have some sort of optimality locally, but they're also having trust,
Yes.
small or sparse. And you are going to have to then counteract that by changing like the topology or by
Yes.
changing your metrics.
Right.
So, you know, can I set up a game?
Well, it seems to me like this system has a bunch of algorithms.
Right.
Right now, we just have path algorithms, but one could also imagine easily adding to it algorithms to do sensitivity analysis,
Right.
other kinds of things. I haven't, you know,
Because the old guys have done, I don't know the data, but they have done sensitivity analysis of certain spot programs over several settings, like the classical one, the capacity, you know, again, using different kinds of operations. But they have not done it with 2 or 3 methods, which is what we have here.
it would be interesting to look at generalizing that sensitivity analysis. See, what is the most general sensitivity analysis algorithm we can think of? It might not work for all semirings. It might have some constraints there.
Okay. Any other questions? No social network questions?